Jacob, Deva, Racusin, and if Ace joins us, then Ace will be here as well. They're with New Frameworks out of Vermont. I've been privileged to know these guys for about a decade. It's always great to reconnect. It's always great to see what they've been involved with in sustainable building. They're always pushing social equity and diversity just as hard as they push building science, and they push building science with natural materials really hard. It's really exciting that they're going to be here sharing about what they're doing with bio-based, panelized materials and building assemblies, trying to make healthy housing affordable and accessible to all. Garrett Johnson is with 100 Year Materials. He's the founder of 100 Year Materials. He also works with Evolve Builders. He's the chief researcher there, developing non-toxic, carbon sequestering building materials from locally sourced, annually renewable resources. He works as a designer and high-performance envelope detailer at Evolve Builders Group. He's been instrumental there in supporting this, and they've been instrumental in supporting his new venture, 100 Year Materials. Garrett looks at the infrastructure we build through a lens of intersecting systems, the natural world, and human well-being within these limits. He believes transitioning the construction industry from one based on intense energy and toxic materials to one based on circular, agriculturally grown sources can not only be a way to help heal the planet, but also the social environment we inhabit. And Sam Kodratsky of Savick, he's the founder of Savick, a family-owned company based near Edmonton, Alberta. They work out of a shop in a farmer's field. Their team of carpenters specialize in prefabrication of light wood frame structures that are insulated with chopped straw. The Savick team enjoys building ever more challenging and larger structures that are both designed to store carbon and serve their purpose for centuries. So we're going to have two presentations, and then we're going to have a little break, and then Brianne, I'll introduce her later, is going to lead a panel discussion, and it's going to be awesome. All right, guys, go get them.
Yes, hey, one thumb up. All right, great. We'll take that as a go. Here we go. All right, thanks, y'all. It's a real honor and pleasure to be with you. I will not take any more time with any more prelude or introduction. I'm going to give you a whirlwind tour of what New Frameworks has been up to. I can't actually see all of your faces because you're very, very small in my window, but I'm expecting there's a bunch of you who I've seen before. I've attended this conference or these gatherings in years past, although it's been quite a long time. So nice to be back with you virtually. And let me let you know what we have been up to in the last number of years, particularly in our journey moving from a custom service provider, custom builder into a manufacturer. So the motivation behind a lot of the problem statement that we're responding to here is around social and ecological justice. That's why our company exists, and so what our primary mission is in our work. And so we see the role of materials, and particularly the use of straw and bio-based materials, as a really critical component of addressing these really core sort of global and hyper-local problems around climate and the associated ecological and social harm that comes from climate imbalance. Typically in the built environment, we see on the left side, the main approach here is to just do less harm, to try to reduce the amount of fossil fuel consumption and emissions that are released from developing buildings and using buildings. And we operate from a thesis that we need to do more than just doing less harm, that zero itself is not a sufficient goal. We need to do proactive good as we are in the pursuit and process of developing human habitation. And so that's where working with these natural processes, natural flows of carbon from the atmosphere into biologic and soil systems, that we can do a lot to help support and encourage that transfer of carbon through the materials that we use and the investments we make as an industry into land-based agricultural and forestry sectors. So that's the big thesis. And so again, we've sort of developed not just our initial practice in working with straw, but really this pivot into manufacturing panels around this thesis that we need to find where these carbon flows are already coming out of sustainably managed forestry and agricultural systems. And rather than letting that carbon biodegrade and go back into the atmosphere, we use those flows as the primary feedstock for the insulation we're putting into our panels. This should all be relatively familiar. I'm speaking to a hometown crowd of straw enthusiasts here, but just to put the point on it as to how we see as manufacturers engaging in these sort of global carbon cycles and partnering with these industries in forestry and agriculture to organize where the flows coming out of those systems can be flows coming into our system. That's not just like our little microcosm idea in the Northeast, or even just among us straw bale enthusiasts in North America, or even globally, that this is actually a thesis that is central to the recommendations that came out of this UN report. I strongly recommend, if you've not yet read this UN report, it is absolutely worth your while. I normally don't go around recommending UN white papers as a point of like inspiration, but oh my God, was this one incredibly inspiring and identified not only the critical role of materials, as a source of emissions and a focus for their reduction, but the role of regeneratively developed bio-based, ethically produced bio-based materials as being central to that strategy. So really helpful to see how our work is placing within a multi-sectoral global context, that we're actually incredibly valuable in the work that we're doing and working with bio-based materials in the built environment. So for us, we've been building, 1 to 3 homes a year, maybe 1 to 2 from scratch, plus renovations and smaller projects. For the first, 15 years of our company's existence, we formally were started in 2005, although we'd all been working in the natural building space going back to around 2000. And so one of the main motivations for us in switching over to panelization was to have a greater impact in the work that we were doing. We were getting really frustrated and somewhat burnt out by putting an incredible amount of resources into building just 1 or 2 projects at a time and only being able to support 1 or 2 families at a time. And in switching over to panelization, being able to have much greater reach into many other projects without the requirements of doing full general contract services and having the projects be completely customized every time. We've seen this dramatic increase in the number of projects that we're able to touch on an annual basis. This year we'll have 15 different homes and buildings that we're going to be supplying panels for. So that was just to give a sense of scale and the extent of our impact as we've switched over into manufacturing, why that was a really significant motivation for us. Another motivation was cost. These are US dollars, so was that 70 cents to the dollar? You can do the math really quickly in your head if you're so inclined. What I'll say is we've reduced the upfront cost per square foot for our buildings by roughly 1/3, give or take, compared to what custom new construction costs. And we're definitely not at a point where we feel really happy with where our pricing is. There's a lot more we can do as we continue to optimize our manufacturing process, our design process for our pre-built homes, so on and so forth. But for us to be able to deliver a non-toxic, high-performance building built of all regionally developed or primarily regionally developed materials for under $400 a square foot US is, we feel really excited to have tunneled through some of the stickier cost barriers that are generally associated with custom construction, particularly in the residential space, particularly with smaller homes, which get proportionally more expensive than larger homes. Sorry for the fuzzy graphic here. The point here is really to say, another really significant motivation for us in making this pivot, not just increasing our impact from a climate basis, but also to address this rapidly burgeoning housing crisis that we found in our state. We're in Vermont, in the northeastern United States. This is indicative of communities all across North America, rural and urban alike, but certainly rural communities facing infrastructural and housing shortages and underinvestment. And so we're looking at many thousands of units of housing that Vermont technically needs to produce to be able to adequately house everyone within our state. And we just did not feel like custom, residential construction was going to get us there, at least for the sake of how our company's investing into this effort. That was another drive around our impact, was not just addressing climate crisis, but also housing crisis. The deep irony here is that we're in a poly crisis. We could add social crises and inequities. We can add biodiversity. There's a bunch of different crises we're struggling with as a global society right now. There's a particularly sticky nexus with housing and climate, where if we were to look at the emissions of just looking at all of the low-rise residential construction built in the US in 2017, multiplying that by the average emission, embodied carbon emissions, and only just the material carbon emissions of those buildings, we're looking at a plume of emissions that is larger than multiple industrialized countries, right? So we're This is an enormous scale. That's 2017 numbers. So if we're now looking at dramatically increasing the amount of square footage, we can see this potential conflict between addressing these two different crises, where in trying to produce all of this housing, we could be creating a dramatic acceleration of immediate term carbon emissions. And we can't do that. So we need to find other ways of addressing both of these crises with harmonized solutions. And that's a really strong motivation for us being in this space. That's a really huge motivation why we're continuing to build with straw, because when you look at the mechanism of straw to effectively store atmospheric carbon that's been photosynthesized into the production of food, and then using the byproducts coming out of those food systems and stopping the carbon cycle in which that straw would biodegrade or be burnt and go back into the atmosphere, and instead banking it into buildings, we see that as a really critical near-term solution for carbon reduction that scales effectively with this scale of housing development. So this is how we can see aligning solutions to address both of these crises at the same time. And it's really important to be able to wrap our arms around that and understand that, quantify that, communicate that. We actually need data to be able to get a sense of like how effective are we in doing this, and where are the areas we need to focus on, and what are the knobs and dials in the design process we need to turn. I feel really honored to be part of Builders for Climate Action, based out of Peterborough, Ontario. That's behind the BEAM tool. So in addition to kind of co-developing this tool and doing a lot of education around this work and research behind the tool, I'm also with the new frameworks using the tool, and we use this really actively in the process of developing our prefabricated buildings to get a really clear understanding of, okay, if our goal is to have a building that is net storing of carbon on day one of operation, what is everything we need to do in the design process to facilitate that? So that was quite literally a data-driven development process in the design of our prefabricated buildings, is to ensure that they would be carbon storing at the beginning of operation, and using data structures that actually make this possible. It's hard to overestimate, hard to oversimplify how important it is to have this data, to have a tool that actually makes the environmental attributes of straw and hemp and these bio-based materials quantifiable and visible and comparative to other more industrialized building materials. It literally can be the difference between them being seen and used or not, let alone for someone like us trying to optimize around their use. So it's a really important part of the overall conversation, both in making design decisions and then communicating the value of these materials back out to the market. And it's not just about carbon. I want to be super clear. That is like a primary motivator for us, but we recognize, nothing exists in isolation, certainly not carbon cycles, certainly not the impacts of increasing carbon dioxide in the atmosphere. So it's of equal value to us to be recognized the non-toxicity of working with straw. The fact that we can use an insulation material that doesn't require toxic binders and treatments and petrochemicals and additives is actually really significant when you look at other, primary industrialized building materials that tend to make up the fabric of our built environment, let alone their high performance characteristics. So everything we do is built to high performance standards. It's super insulated, continuous installation, high levels of durability, air tightness, all the things, let alone fire performance. So again, I'm sure I'm preaching to the choir here in terms of recognizing the attributes of these materials. I'm bringing this up to organize that we have something, to be able to identify and again quantify and document and report out the stacked benefits of these materials is really answering a whole lot of competing needs that I see in like the broader world of the built environment right now. The fact that we have these solutions is amazing, but how we're able to communicate them and get them visible and quantifiable in the market becomes a really important part of spreading this work. And as we've moved into manufacturing, that type of communication, that type of market development and market transformation has become an increasingly large part of our work, because it's not just the keeners who want their own custom built straw bale that need to know about this. It's now a much broader market. Okay, so that's all the basis. I know I speak really quickly. Don't worry about holding on to everything. We can bring any questions that show up in the Q&A. I just want to keep moving. I just wanted to give you some of that basis. So now I'm going to show you some of the work that we're doing. You had an understanding of what's kind of behind all of that. So our panels, we've adopted a model of essentially double stud construction with straw, non-structural straw insulation. We're basically building fluff build boxes, and the fluff we're using is straw. We went with this approach partially because we were an active building company and transitioned into being a manufacturer midstream, which is really different than starting a manufacturing process from scratch. So this was a very familiar, recognizable, code compliant type of an assembly for us to be able to pivot into immediately without needing 10 years worth of R&D and a huge capital raise. So we made the transition into manufacturing in real time without any capital investment beyond what we were able to generate within our own company and within 1 year's time. So that was a huge part of the design basis of something that's really simple, really familiar, really easy, low barrier to manufacturing development was an important part for us. And so we take these, boxes, they're stuffed with straw. We have air barrier of some ilk on the interior, and we've got sheathing on the exterior. And they form together as a panelized approach to wall construction. And we'll look at floors and roofs in a moment. And so you can see sort of carve up a building into panelized sections. The rough openings are developed from the negative spaces where the panels connect together. And the design process sort of maps all of these out in a very, very specific and explicit way when we take a 3D model of the building and then quote unquote panelize it. It's the overall approach here. It's the general reference model. So just to give some visualizations, this is better explained by actually looking at pictures. So we're getting all of our straw from Aurora Farm. They are a really critical part of the Vermont food shed. They're one of the only grain producers, and they're an organic grain producer in the Lake Champlain watershed. They're also in a really ecologically sensitive part of the watershed. So the fact that they're an organic grain grower is actually really important for larger ecological value to our region. So that's where we're getting the majority of our straw. A few other suppliers that we'll work with as well. The straw, you can sort of see the lake right in the background there. It's the straw getting cut and tedded. It gets baled and brought into our shop in Essex, Vermont, which is right outside of Burlington. We store large volumes of straw in our shop, which makes for some really interesting challenges around dust management and air quality management, but is also a really wonderful environment in which to have a manufacturing facility with a big stack of bales in the back. Again, we have a full service architectural firm within our cooperative, and so we are able to work with architects and builders, and we're doing custom panels for other architects and builders, working with their architectural designs, and then, as I was mentioning earlier, panelizing them, developing, going from the design to fabrication process of creating shop drawings for every individual panel based on whatever design that we're working with. Here, the team is screwing together the tops and bottoms of the panels that then get fitted into the steel frame. So that's a top going into the back of the steel frame. The straw is then compressed. These are relatively old photos. We have some updated manufacturing process at this point, but still gets the general idea across. Straw gets compacted into the frame. Once it's filled, the frame gets pulled out and all the straw gets cleaned up. And now we've got a pretty straw insulated wood framed structural panel. We are doing floors and ceilings and weird shaped walls using primarily wood fiber insulation from Timber HP. It's actually a blend of wood fiber and cellulose insulation that we inject into the panels. So I'd say the vast majority of them are straw, but we're also using this sort of flexible form of insulation for some of the weirder shaped panels where working within the module of the bale isn't quite as effective. For panel projects that have a plastered interior, we're putting the base coat and the scratch coat of that plaster on in the shop, which after spending the first, maybe not quite decade, 7-8 years of my professional career as a plaster contractor, the novelty of being able to pour buckets of plaster horizontally and screed them onto a frame is just fabulous. My rotator cuffs are grateful the rotator cuffs of my crew are grateful that we have figured out how to do this horizontally and not just vertically. All right, so moving on to loading, shipping, delivery, everything gets flat packed and put into trucks, especially if they're going really far distances. We are right near a light rail, a rail facility, not so light, heavy rail. And we ship by rail when possible, but usually the issue is on the other end, particularly for rural communities where logistics going from rail to site are more challenging, but we do have that option as well. We also do general contracting services of our own pre-designed and fully panelized small homes. In those cases, we're just towing them across town or around the county. And then they get installed. And so we've sort of designed these intentionally to be relatively small and easily maneuverable with smaller equipment. This is designed to be able to scale down to smaller forms of construction. We're doing larger wall assemblies, just doesn't always work to have crane mobilization on many sites or for many budgets. In this case, we're looking at the installation of floor frames, floor panels for one of our pre-designed, pre-built homes. I'll talk about those in a moment. The wall panels tip up, they screw together. We work with a structural engineer who's we have a strategic sort of partnership with, who does all of the structural engineering. So every fastener is spec'd and placed intentionally and designed to make construction really, really quick. It's another really big benefit we've seen. Here's an example of where a cellulose insulated or wood fiber insulated gable panel is sitting on top of the straw panels, ready for air barrier continuity and integration. Floor assemblies are pre-built. In this case, I believe, yeah, that's a second floor assembly is pre-built for one of our really small ADU projects. So for our own pre-built homes, we're panelizing absolutely everything possible. Lots of detailing going into air barrier transitions. We'll talk a little more about that. This is just giving you a quick close-up of what that looks like. And we do commercial structures as well. This is for a large commercial kitchen dining facility program center for a farm education center in upstate New York. And just was so happy to see that they wanted to see a truth window. So it's just nice to know that the spirit of the truth window still lives even in like modern commercial panelized construction. I'll show some finished photos of this project in just a moment, but the other thing to highlight here is that, you know, this is a commercial facility. Interior plastering was actually not what they were necessarily looking for. And so these panels are aligned with the typical approaches of double stud high performance construction you might see within, in this case, an airtight vapor variable membrane on the interior instead of a plaster membrane. So there's more flexibility that we're finding with different assembly approaches than when we're doing custom construction, which is really exciting. Utilities are a big one for our pre-built buildings. I'll move through this relatively quickly, but you saw before where we had a design goal of being negative carbon emission going into operation. And part of that was moving away from concrete. So whenever possible, we're placing our homes on helical piers, which creates some interesting challenges in cold climates or bringing utilities in. This is still in development, but gives you a sense of how we've been managing this through, in this case, using a culvert entrance, an insulated culvert entrance, for when we need to safely bring utilities from subgrade up into the building. Not my favorite material in the world, but there are still applicable, good, reasonable applications for spray foam in this world, and this is one of them that we found. Ultimately, creating a pretty sequenced and efficient coordination of subtrades throughout the entire process, which is really different with panelization than it is with custom construction. So we've had to learn a lot about migrating to a very different construction sequence and workflow process, including building service cavity floors instead of just walls, where we need that plumbing to all exist up and above the sort of formal contained enclosure of the floor. So really interesting series of problems that we've gotten to solve or continue to work on solving. That whole service cavity process has been really all the more valuable in panelization. Again, to disaggregate the sequencing of trades and to really make sure that we don't have to dig back into the panels and deal with quality control management. So being able to just run these utilities in the face has been terrific. We don't have that many utilities in certain buildings. It's just a little bit of wiring. Then we've been able to manage that really effectively with thickened baseboards. This is an old technique even that we're using in our custom construction process with plastered assemblies, and has become all the more relevant and useful now that we're building with a panelized environment and we're trying to really reduce the amount of customization of the walls themselves. I do want to stay on the air barrier topic a bit because I am a building science nerd and it's such an important part of the durability and performance and protection of these assemblies. I feel like straw is really not only best, but requires being applied in a high performance context to really allow it to do its best job and to receive the durability value that it has to bring to the table. So here, plaster is still remains my all-time favorite air barrier solution. So it's nice with this material to be able to integrate that. You can see there's some tricky detailing here where there's some let-in framing that'll be mounted onto the panel, and we have a transition here from the plaster system to an air barrier back to a plaster system to accommodate for that. It's the nice thing about being able to do design in advance is once it all goes together in the field, it's exactly the way it should be. We really attend to these transition details between plaster and the edges of the panels so that there can be continuity across to the windows and across to the ceilings and other assemblies. Those edges of the panels are what we call planked in the field, not unlike drywall taping, if you will. So once the panels are installed, that rough coat just gets finished and connecting across those different the different panels, the different sections of plaster. And then again, we've got this high performance tape that makes for a really good transition from plaster to wood assemblies. It's a fleece tape that embeds into the plaster, but then has a permanent and flexible connection via its adhesive to the adjacent wood. So just an example of how we're able to maintain the air tightness requirements for our systems. And then it all gets finished out to look nice and pretty. Plaster is the best. All right. So speaking of finishes, I'm going to move through this very quickly. Just kind of wrap us up here with what the end product looks like. We work with a lot of locally sawn wood, and we have an abundance of local wood purveyors or sawmills. Actually, not an abundance. It is a dramatically reducing industry, unfortunately, in our region, but there are still a number of mills that are kicking around that we are investing in by purchasing their products for our as much of the wood components of our projects as we can, including the exterior finishes. You'll notice this is board and batten, and part of that is because it is really inexpensive and easy for wood mills to create sort of simple wood forms, as opposed to like a beveled clapboard is much more expensive, and there are fewer mills that can produce it. So some of those details are designed literally around the regional material supply available to us, and that really informs our architectural design as much as possible. All of our buildings are all electric. We have a pretty firm commitment to not putting any new fossil fuel equipment into any of our projects unless absolutely necessary. So happy to have inverter-driven cold climate heat pumps available in abundance at this point to have that be a standard part of our process. The finishes here are all relatively simple, just pretty nice. This is one of our sort of smaller kit homes that you're looking at right now. Yeah. This should all be pretty familiar for all of you than doing really pretty plaster and wood projects for many, many, many years, just with flatter walls and a little more rectilinear than when we were building in decades past. Compact design has been a fun challenge, emphasis on the challenge, but actually also on the fun. So as a mechanical designer, it's actually been one of the largest challenges of this entire process of prefabricating small homes. Is actually getting equipment small enough and getting the noise of the equipment to be quiet enough and getting the sort of everything to scale down appropriately when we're building housing, say under 1,000 square feet, 300 square meters or so. It gets the mechanical challenges get interesting. So happy to talk about more of those in the Q&A for those of you that are interested. But yeah, just some more eye candy of kind of what these buildings look like. I realized I probably skipped over the really important part, which is to say that we are supplying our panels both as custom panel fabrication for other designers and builders, as well as our own line. I'll stop on this for a second, as well as our own line of pre-designed and prefabricated small homes. So we have a line of, I think, 5 different sizes, from a teeny little 400 square foot ADU up to our largest right now is a 1,400 square foot 3-bedroom home with a larger model that will be coming out next year. So when I talk about my prefabricated and pre-designed homes, that's what I'm talking about. I wanted to give you some of the finished shots of that commercial facility and how that this is our design team on the right, the owner of the farm in the center there. Really nice, probably one of the nicest, best detailed truth windows I've had the opportunity to be involved with. This is what that facility looks like finished out in the interior. So it looks relatively conventional. You really wouldn't know it's a straw building were it not for the truth window, which is why he felt pretty inclined to keep it in there. And then, yeah, it finishes out really nicely on the exterior as well. So it's just good to be able to, it's for us to be able to bridge into commercial applications. The panelized solutions has been a really exciting part of the development of this work. So the last thing I want to just connect with is how we've worked to scale this process. In addition, moving from being a custom builder to a manufacturer, we recognize that to really be able to achieve our goals at scale and addressing these poly crises, the sort of typical version of manufacturing is just to grow in the scale of our facilities and our production. We realize that is not our interest. That's not really what we want to do. It's also not a model of economic and manufacturing development that we really feel is going to solve these problems. So our approach has been actually to develop the SEED Collaborative, which is a network of helping stand up other panelizers across North America. So we developed essentially a workforce development and training and technical assistance program where we help other companies become panelizers. And so that started with 2 companies in 2024, Rare Forms in Massachusetts and Building Integrity in Missouri, that within that first year started fabricating and serving the market and building homes within a year, which was really exciting. Sort of a similar timeline and pace that we achieved in our initial transition. It is now, since that first year, we are now very much resource sharing, co-developing marketing materials and performing marketing services, collaborating on design processes, working on manufacturing upgrades. So it's gone from just us, helping them to get established to now a network of producers that are all sharing strategy and co-investment, which is really the path we see towards rapid expansion of this work in more of a horizontal, decentralized framework rather than one of us becoming the largest panel manufacturer in North America. So heading into this year, we have 3 others joining us in Maryland and Colorado and Washington State. So we are really thrilled to now have this expanding group of panelizers in development to create a much broader network across the continent for spreading and developing this work. And so the last thing I'll say is a shameless plug here. The other form of scale that we've been working on is New Frameworks has worked with the Mass Design Group and a few others to develop the Bio-Based Materials Collective. This is a North American focused organization. Mexico, US, and Canada are all represented, of over 400 different stakeholders across not only architecture, engineering, and construction, but throughout the manufacturing sector, as well as farmers and foresters and forest product advocates, all working collectively to scale up the use of bio-based materials in North America. There's a series of different working groups that are pushing efforts along in academia and education, as well as in the regulation space, the technical space of product development, so on and so forth. So if you are interested, boy, would we love to have you join us. And if you're interested in joining us in person and are willing to adopt the risk of crossing over southern border into the US, we warmly invite you to join us in Burlington next month. And that is 30 minutes on the nose for me. So I will stop there and pass the mic. And since the camera is still muted, if anyone is saying anything that I should hear, you might need to unmute the laptop.
I'm just trying to share my screen here. But Jacob, that was an amazing presentation.
Yeah, really excellent.
I can tell the audience right now that ours will not be as good as that, but at least I was able to enjoy a nice half hour this morning. No, it's really, really inspiring. But yeah, my name is Sam. I'm the founder of Savick, and yeah, I really enjoy building straw panels. And yeah, Garrett and I are going to talk a little bit about kind of our own operations, and then a little bit more specifically on how we can comply with building codes and a regulatory path so that, yeah, the masses can be building with straw. Maybe Garrett, you'd like to say a few words before I jump straight into my portion of the slides here?
Sure. Yeah. So my name's Garrett Johnson. I'm the founder of 100 Year Materials, and we're making more of the specific individual components of a building assembly that hopefully will end up being integrated into some of these natural building prefabricated assemblies So there's some form of synergy going on there. We're also focused on producing things from circular, annually renewable agricultural fibers.
Right on. Well, I'll jump right into it. I haven't been doing this for very long, only been building straw panels near Edmonton since 2022. And most of this has been single family residential projects, agricultural projects, but starting to see a growing interest in the commercial side and the multifamily side. So having to learn a lot about building science, understand what we currently know of the technical capabilities of straw, do some more research on straw, figure out exactly what are not only the highest performing, but like the safest ways to work with this organic material. And then figure out production. That's the big piece right now. There's, I think, a lot that we can do with a very basic material like chopped straw, which is very similar to straw bale construction, except instead of long fibers, we're actually cutting it down to anywhere from a centimeter to 2.5 centimeters in length. You can kind of see in one of the images there, it's not quite as small as sawdust. It's kind of a step above. It's more similar to like cellulose insulation, where if we look at that again, that supply chain, it's, any, wheat, barley, oat straw will do as long as it's dry and free of impurities. That can come mostly, in our case, from our family farm or from any number of the thousands of farmers that are in Canada or in North America. And we then are trying to plug in a bit more into a typical, more so industrial agricultural production, where instead of a bunch of small bales, it's working with big round bales, big squares, where you're getting 500 to 800 kilograms of straw and one nice little shippable component that we can then store on the farm and then call up the local tub grinding contractor, and in a matter of a half hour he can chop up enough straw to basically do 2 houses with, and we can then store that chopped straw in a tent, and then when we are building the panels, it gets blown into a closed cavity with standard insulation blowing equipment. So the biggest variable that we're playing around with chopped straw is actually the density that it gets installed, because with all the thermal testing we've done, we found there's kind of a sweet spot around that like 4.5, 5 pounds per cubic foot, where you're getting pretty impressive insulation values, like over R4 per inch. But at those lower densities, chopped straw is more prone to settling. So we are having to increase that based off of whether that straw is being blown on site or if it's in a prefab panel where there's a bunch more vibration and additional risk for settling. So right now we're insulating our wall panels at around, close to 7 pounds per cubic foot. So that's not quite as dense as like a straw bale, but it's getting up there. These panels are definitely, filled with lots of straw. And you do see the R value per inch dropping off a little bit at these higher densities, but because straw is so widely accessible, we just make the wall a little bit thicker, and we can still get, some pretty interesting high-performing assemblies without necessarily the highest costs. And so at the end of the day, like, these panels are being built by human beings. It's not like a computer controlled manufacturing facility that's like one stock keeping unit. We can only build one thing. It's pretty easy to customize how much straw is being used in a project, what application, whether it's a floor or a roof panel. But we have gravitated towards certain assemblies that we know work quite well for the kind of projects that we're serving, which are mostly in cold and very cold climates. Like the biggest risk factor we have around here where we see building failures is moisture during the winter and the nice hot humid air on the inside getting into the wall and not having a way to get out before it starts causing problems for people in the spring and even into the summer, where with conventional construction, even with like super detailed, poly vapor barriers, there's still big issues that folks have. So we've worked with mainly plywood as a vapor barrier, and it's something that gives our panels a lot of structural rigidity, but also it's very easy to make these panelized enclosures incredibly airtight just by simply taping the seams of the plywood and any penetrations that are going through it. And it's very easy to verify that it's been done correctly. So you can kind of imagine these big, plywood on the inside, wood fiber on the outside with a weather resistant barrier being delivered to site in these huge rectangles. They can be up to 30 feet long, 12 feet wide. They can weigh 4,000 or 5,000 pounds, and they all come together. And those dozen connections you do on site are then taped together for airtightness, structurally connected to make, what I think are pretty interesting buildings. And that's primarily the focus of our company is to build stuff. I started Savick to be a solution for storing carbon in the built environment. And we certainly have customers that are interested in that, but most people are coming to us just because they want to build something, and we want to make straw accessible for more projects. And part of that is knowing our stuff when it comes to planning projects out, so we can offer structural engineering services for projects. We can help coordinate certain envelope details, try to incorporate different window manufacturers' preferred details with the siding contractor, and try to make sure everything plays nicely with the material that will rot if it gets wet. And so it's going through the fine-tooth comb on every project that we're doing to make sure that things are actually going to perform as they are designed. And with kind of the pieces of the puzzle planned out, we get to then focus on the actual building, which is the fun part. We can send panels across Canada without too much difficulty. And another thing we found is helpful on these straw insulated projects is there's often parts of the project that aren't insulated with straw. And so we have gotten pretty good at just building uninsulated panels to kind of support not just interior framing, but the structural systems, and have things come out as one package so that you can go from foundation to a dried-in building in a couple days sometimes. So again, this works well with our smaller residential agricultural projects, but trying to plot out a pathway where we kind of go from these more artisanal projects to actual scaled, big construction, which is kind of the main topic of this presentation, is saying, all right, we know we can use straw on single family, light commercial without too much difficulty. What is it going to take to go build like thousands of square meters of panels on all kinds of construction that we know we can do it? In other parts of the world, they do build, apartment buildings with straw panels. Like, it's not a limiting factor from the technology side. It's just figuring out how can we get production to a point and compliance to a point where we can start wrapping, mass timber structures with the straw insulated facade. How can we do even up to 6-story tall buildings with, structural straw panel systems? Doing light industrial work. There's all kinds of, projects that come across the desk that are very exciting, and it's just figuring out now, how do we actually get the ball rolling and actually build it? So I'll hand it off to Garrett here, and hopefully he can flesh out kind of that idea.
Thanks, Sam. Really great to see you talk about the expanding the scope of those buildings. I really would love to see some mass timber and straw buildings in Canada. It's such a cool format. So 100-year materials, we are developing components of assemblies. We're developing building materials, and we have a focus or guiding principle of making them carbon sequestering, annually renewable, non-toxic, low processing energy. So we want to have carbon negative products, but we also want to have very low input energy. For example, a wood fiber insulation manufacturer may have a carbon negative footprint, but if you take away the carbon sequestration portion of the equation, they're still emitting a fair amount per square meter at 1 RSI, which is like the standard for an environmental product declaration. So we want to both have an input energy that's less than a conventional product like extruded polystyrene, but also have it be carbon sequestering. And we also want our products to be biodegradable. We're looking right now at drop-in replacements, so making something that's familiar to most builders, so we don't have to reinvent how we're building things. And ideally, those materials are coming from circular places, so the leftovers from food production, just like Jacob mentioned, and Sam is also using that. So next slide. The first product we're looking to commercialize is a rigid insulation. It's bio-based, non-toxic, comes from a rapidly renewable agricultural feedstock, straw, and there's a wide variation in potential thicknesses. So unlike the domestic wood fiber panel products that exist in Canada, there's no limit on the production thickness. They can be greater than 1.5 inches. They can be 3 inches, 6 inches, just because of the manufacturing process that we're using. And we've started creating some samples at industrially matched facilities. This image is taken at Initech, Alberta, where I actually met Sam. It was awesome to go see him and visit the facility there. And they did some preliminary testing on R value while I was there, and it was currently tested at R 3.2 per inch, which is quite good for a fiber insulation board. But our target is trying to get that up to 3.4 per inch so that we can have an R10 panel at 3 inches thick that will satisfy a single layer for exterior continuous installation required for homes that are heated with electric heat. Next slide. That's a photo of the 4x8 sheets that we made at that facility. And you can see the little square sitting on top of it, which is about the size that I was making in the laboratory last year and up until now. Next slide. We're also developing a blown insulation, and this would be, again, 100% circular feedstock and is a byproduct of producing the board product or the other products that we're making. And it's free of dust and intended to be a direct replacement for commercial blown cellulose insulation. So being able to use conventional blowers that are designed to be used on site for a conventional builder. And this summer we're working with Enercan to test both the R value and the settling properties to understand that optimal installation density that Sam was mentioning previously. Next slide. We've also developed some exciting prototypes for an annual plant-based OSB product. So this would be intended to be a structural sheathing. And I traveled to Quebec earlier this year to a facility in Trois-Rivières, and we made some 2.5 foot by 2.5 foot samples that you can see there. I got a new phone and I'm able to take some higher quality images than my old iPhone 6 recently. So I'm very excited to share that. And so this, again, intended to be structural sheathing, similar to the company Planted in the United States, but I'm using non-toxic bio-based adhesives there. Next slide. Just another photo of that to share. Next slide. And this was super exciting. Just a couple of weeks ago, developed a new prototype for a bat insulation. So this would be similar to hemp wool or the Nature Fibers Profib bat, similar densities and production methods, again, using annually renewable fibers, plant fibers. Next slide. And this is a video of it looking squishy. And if, not sure if Michel is there yet, but he was bringing some samples of my materials to the conference. He's running late, so they might not be here yet. But if he is here, feel free to, Michel, feel free to pass those things around. Or if they already have been, that's great. Next slide. And we have a few other irons in the fire. One of them, something that's interesting, an interesting concept right now, is a bio-based intelligent membrane. So leveraging some of natural fiber's ability to both reject or transmit moisture depending on relative humidity. And we're also hoping to get some fire-resistant rigid boards that would be useful for commercial spaces or multi-unit residential where you need some better performance for fire. Next slide. So there's a whole bunch of options possible. There's this palette that you can play with and develop exciting products with different technology platforms, but to truly scale these products, because that's the goal here, is to proliferate them to the mass market. In my opinion, get everybody on board. We need consistent supply chains, low energy manufacturing, so reducing that embodied carbon of the manufacturing process. We need to ideally use existing machinery so we don't have to reinvent the wheel. Looking at long-term durability, we don't want to have to have a bad perception of these products from the public when they initially get released. We want reasonable costs. Again, the goal is to try to make these cheap and available to everybody, democratize natural building materials, and minimize the risk for capital investment. So try to make something that's possible to enter the market in without a major risk of things falling apart and losing dozens of millions or $100 million or something like that. Next slide. And so that last point is something that we've been excited about recently, is that some of these products, they're produced on the same technology platform. So you can have a single investment for a manufacturing line that can produce at least 4 different products, and likely more, just limited by creativity and inventive ingenuity for what builders need and what we can produce. But these 4 products that we have right now can be produced with a single manufacturing line, which is really exciting and important, because in those early stages of starting a manufacturing company, especially if you go really big, really fast, your supply is likely outpaced by the demand for a significant period, and you're just dumping money into producing a single material or product with an oversaturating a market, and you're making a huge risk for a bankruptcy, which I've recently heard that Timber HP has voluntarily filed for Chapter 11 bankruptcy. They're likely not going to go away forever, but that's still something that I would want to avoid. So in this situation, you can have a small line at a lower entry scale than timber HP, and you can share that manufacturing time between multiple products while your whole demand scales, and then have regional manufacturing facilities that can produce specialized products or enough demand for what you can serve within your region. Next slide. And I truly believe this is a better way to insulate beyond any performance characteristics. It's truly the only way to have both zero carbon buildings and zero energy buildings. With all other insulation products that have a global warming potential above zero, there's an optimal point where adding more insulation can actually be detrimental to the environment, or at least not creating any more benefit. You might be reducing your bills moderately or having a more comfortable home. But if you're heating your home with a heat pump, the extra energy needed to maintain your home's temperature between R4 and R8 is really big. That's a big deal. That's awesome. But the difference between, say, R20 and R24 is negligible. It's very little. So in this graph, you can see a bunch of lines where adding more insulation can actually increase the overall combined embodied and operational carbon emissions. And so those two lines shooting up are the worst emitters. They're kind of the old format extruded polystyrene boards. And then those lines down the bottom that have plateaued are pretty much every other insulation product out there. So after a certain R value in your wall, you're not doing a whole lot of benefit for the climate. However, if you have a carbon negative insulation product, you can just keep adding insulation to your building. You can get to passive house levels and beyond, and you're both reducing the operational carbon emissions and the embodied carbon emissions. So you can have a building that's carbon negative for the entire lifespan of that project. Next slide. So Sam and I assume Jacob and everybody else in this field is asking everyone to imagine proliferation of these products. Imagine entire neighborhoods built from these methodologies where every home is insulated with annually renewable non-toxic materials. Every home is super efficient, built to last generations, like Sam was mentioning. The whole neighborhood acts as a massive carbon sink that we want to protect. And ideally, everybody just thinks this is normal. And that's the end goal here. Sam? Oh, you're muted there, Sam.
I said a bunch of smart stuff and everybody missed it. I was just thanking you for that portion of the presentation. I always love hearing what you're getting up to. And yeah, seeing those samples in person was, really encouraging. It's not as far away as I think some people think. Like this kind of stuff is very, very close. And so now it's thinking more so, all right, let's get going here. Let's figure out how we can actually build these neighborhoods. And production is a big piece of it. It's something that consumes probably 80 to 90% of my time, is just figuring out how we're going to build what we've already been approved to build. We've already found customers for, we've already gotten permits for. It's just execution is a huge, huge, huge piece. But over time, I think that will start to shift when we're looking at the proportion of energy being now put into, all right, we got these production lines established. Maybe we found more efficient ways to build these panels. We need to feed the beast. We need to get projects through our company. And a big piece of that is, is marketing. It's saying, hey, homeowner, this is a better way to build for these reasons. Here's this literature that shows off that, just because you build your house out of straw doesn't mean the big bad wolf is going to come. And then the homeowners that you do convince is, yeah, it's a good idea to do this. They need to then convince their local permitting official that this thing isn't going to fall over. And kind of the way that we've been doing that has been through asking nicely. I mean, that's been the main thing. Like sometimes we've had to do like a site specific variance, but if we kind of just make a case and say, yeah, this is, you know, the structure is the same. You don't need to reinvent the wheel there. We're using good products to protect, again, this material that will rot if it gets wet. And we have an engineer who's reviewing the design and accepting some level of liability for it. Then getting the rubber stamp on the building permit application hasn't been that difficult on these smaller scale, you know, residential projects, where it seems insane to me, but there's not even a requirement in the building code in residential to have fire resistance for insulation. Like anybody could put any foam they want into a building. It doesn't matter if it would literally explode. It's like, put one layer of drywall on and you're good to go. Like it seems insane, but that's kind of the environment that we're working in, so we can take advantage of it on these early projects. But we do, again, want to be building more demanding things. And when you start building bigger buildings, you have bigger risks. I mean, and they're not just, you know, arbitrary performance guidelines being, you know, handed down from on high. It's like, we need to think about how to actually make very, very safe, very durable buildings, and spending a lot of the energy there. You know, we can get the regulation stuff put through, you know, with a few $100,000 as an industry, without too much of a real headache. But we need to know like how to actually work with straw in the best way. And I think, you know, kind of those semi-standardized systems, you know, that I'm coming up with, New Frameworks is now, you know, have a package that seems to come together pretty nicely. You know, that is something that is a really important starting point. But when you want to go build like an 18-story tall mass timber structure building and enclose it all, it's like, we actually need to like do some real full-scale testing, like more than just in the lab and go light something on fire and measure how much smoke comes off. It's like, no, you need to go build it and like light it on fire and see what happens. Like that's how a lot of the rest of the industry has had to do this. You can't, you know, go design a straw panel just, you know, using the tabulated values in the wood structural engineering handbook. Like, no, we should go build it and then put it on a huge shaker table and see like what's it doing, and like do real science on these buildings, because we think we know like how it should all work. But I think the construction industry is based off of real evidence and trying to see, again, like how can we make sure that these buildings, they're not going to fall over, they're not going to burn down, they're not going to rot. And I'm very excited to see kind of the preliminary research that's being done on straw by myself and others. But there's still a lot to do in the next decade to really prove that, yeah, we can use natural materials in a big way. And I'll hand it over to Garrett here.
Yeah, so for Sam, there's a certain scope of code that's relevant. For myself, producing materials themselves in residential construction anyway, we're targeting the low-rise situation. There's really just the building code that would apply to us. So every material that you use must meet the requirements of the building code. And that's really the only true requirement, is that you meet the requirements. But what they are is sort of sometimes hazy. Technically, all of the Canadian codes are objective based, and they're based on these functional statements and objectives that are super broad, like will maintain the safety of occupants. And then you have to prove that you can do that. And it's up to the builder to show that you have that compliance. Next slide. At the start of each section of the building code, they have a portion that lists ways to meet compliance for materials. So in part 9.25, there's a big list of ULC standards that the building code has said, we like these standards for insulation products. If you can meet them, then you meet the requirements of the building code. And the way that you certify that you meet these ULC standards is typically done through the Canadian Construction Materials Center, the CCMC. And you do an evaluation on your product, and they say, yes, we agree that the data you've collected matches the ULC standard. You're free to produce this product, or we concur that every region should be safe to use this product, and then your regional regulators won't cause a fuss. That's not the only way to prove that you meet those standards. And ultimately, the final call for whether something is safe in a building is up to your local regulators. And there are a few different paths to compliance that do not require this broad CCMC evaluation. If you have a truly new product that doesn't fall within one of these standards, which is often the case as these standards are quite specific, then the CCMC will develop innovative solutions technical guide for you. And that is very expensive, and it takes up to 2 years. So it's something to try to avoid if possible. Next slide. So the first and easy path that many of you here will be familiar with is an alternative solution. So this is project by project based, and it's dependent on the ruling of local authorities, and there's limited scalability for especially a single product, unitary product manufacturer like myself. For Sam, he had mentioned that, you know, they're getting upwards of should be fine up to like 50 homes per year, and that's amazing and totally possible with this platform. But if you're trying to sell hundreds or thousands of projects per year, it's not really a scalable method of code compliance. Next slide. One way for code compliance in Ontario that I feel like people don't talk about as much is the Building Materials Evaluation Commission. So they have a mandate from the provincial authorities to conduct research on, inspect, and rule on the safety and compliance of innovative materials in Ontario. And they have a flat fee that's an order of magnitude less than the CCMC evaluation for innovative materials on the technical guide. It's a faster turnaround time in the realm of many weeks rather than many months or years, and it gets access to quite a large market. It's Ontario has greater than 30% of the Canadian construction market. In 2024, that meant a BMEC certification could get you access to 70,000 of 180,000 housing starts in Canada. Next slide.
Yeah, and looking at kind of those halfway solutions, like you can get things validated and start building up that portfolio, but in order to have like a real industry, yeah, having a longer term view on regulatory compliance is going to be a big part of natural materials, I think. And so, yeah, like alternative solutions, they're not necessarily a terrible way to go about it, especially for like a prefabricator like myself, like sometimes because we are working on projects in a much more involved way than just supplying one component, the cost of, say, that additional engineering or that additional paperwork really does get absorbed through the rest of it. But if you're just buying, you know, a straw rigid insulation board, and you have to pay for additional engineering, additional regulatory compliance, then it could be prohibitive. So looking at the next evolution of compliance is kind of the theme here, where for us, kind of the starting point is to continue with my previous point of just like, let's really learn more about straw, because that is going to be very informative to the folks who are developing either your CCMC technical guide or even potentially developing a CAN ULC standard. Is what do we actually need to be looking at here, and who needs to be involved in determining that these products that a bunch of manufacturers are putting together actually do perform well. And with, again, our reliance on engineering, it's more than just, say, the straw itself. We are looking at kind of the bigger picture, where it is, how do these panels come together structurally? How do we finish the panels so that they can meet 1 hour, 2 hour fire ratings are required? Maybe do some full scale testing on acoustics. So now instead of just like relying on straw only as like an exterior insulation, what about separating living units in multifamily buildings? How can we do party walls, you know, in a compliant way with straw? And again, really dig down into how we can best work with these materials so that we can communicate it to the building designers and say, architects, please stop specifying this stupid thing. It's really difficult to make it work. If you actually just do these 3 things, all of a sudden, you know, straw is going to be super cost effective to incorporate into your project. And even just making the projects themselves run a bit smoother, and just having that data available to everyone involved, like have all of your effective R value calculations completed for different wall assemblies, and say, energy modeler, please just run with this. You know, here's the testing data. You can go look at it yourself, but you can now almost treat, you know, natural materials as just this other, you know, kind of boring thing. Just not particularly exciting, not particularly scary. Just here's this corpus of data. Anyone with a critical eye can go in and say, yeah, I think it's appropriate to build this kind of thing here. And then that overarching idea will, I think, get funneled into how the actual regulations should be looked at in the future. Because with, again, the product development side of just making straw like super easy to work with, just super cool, is knowing that the straw panels we work with today are probably different than what we're going to have 10 years from now. Probably going to find through this research, through this additional experience just working on projects, we're going to see an evolution of the best way to process chopped straw, the best way to protect these panels from the elements. And when we were getting going with these standards, it kind of locks you in, if that makes sense. Like, you have to have a documented quality control program for a very specific process, and then you're certified to that process. Whereas an alternative solution is looking at more so the performance of what you're putting out. And if you find maybe from one project to the next, we had to change a couple of things to make it even better, it's much more flexible than spending $100,000 on coming up with a standard for a particular product. And then if you want to really change something, even like minor things, sometimes you could be, you know, having to spend additional money another year delay or 2 years delay in getting access to a market, and really trying to think of this as once we know for sure that these straw based products kind of meet the needs of our customers and meet the needs of building professionals, that's when we'll want to certify these plants. That's when we'll want to formalize these production strategies so that it is considered more so like type 2 EPS insulation. You know, there's 5 different manufacturers of that around North America, and they all do it the exact same way. You know, I could imagine a future where we are making chopped straw insulation the exact same way for everyone. It's ubiquitous. It's going to be in the building code, and there's not necessarily going to be this special song and dance that goes along with it. It's just going to be another boring material that we know exactly how to do. But today's not that day. Today is very much still figuring out how to make, chopped straw, rigid straw boards like fit into the big picture. And that's a big piece.
Yeah, absolutely. Sam, you got some good insight in there. The regulatory path of getting to that scaled acceptance is complicated. And there can often be a winding path from when you create a product to getting it to full market. So as Sam mentioned, there's this sort of choice or pinch point where with a CCMC certification, you have to have a totally finalized product and finalized manufacturing facility. If you change any of that, then you're changing the whole system and you're no longer really certified. So once you've developed a product and you've got third-party data showing that it's safe to use and functional, you have a few choices. So if you don't have a manufacturing line, or you still expect some new development in your product, some more iterations or improvements over some period of time, then your choices are really the alternative solution that Sam suggested, or even the BMEC certification, which has significantly less investment required. Rather than $100,000, it's $10,000, which might actually be worth it, especially if you can get some funding to offset that. Once you do have a manufacturing line, then ideally you're going to want to have a ULC standard created already. If you don't, then you're back to the CCMC certification for an innovative solution, super expensive, or you go as if back to the alternative solution and BMEC. And then next slide. The path that we're going to try to take is circuitous, but I think makes a lot of sense, where we start with alternative solutions in the early phases for pilot projects as we're still iterating product design. Once we get some more and thorough third-party data and we're ready to present to provincial authorities, we get BMEC certification, gets access to 30% of the Canadian market, and likely enough of a market that can sustain that entry-level manufacturing line we're looking to make. And by then, hopefully, there will be a ULC standard for a product like this. And I've heard that there's one being developed right now for a rigid board product that is being led by the Canadian Wood Council. So that's kind of our plan right now. Next slide. And we're really just at that first step right now. We're gathering third-party data on the product, and we're still making some iterations. It's at a point right now where we think it's nearly ready to be installing into pilot projects, and we're looking at that for the fall. But after that, we got to move down that line. Next slide. I think this is you, Sam.
Yeah, and so you mentioned that that new wood fiber standard being made by the Wood Council. It's often a few companies that team up on these things. you can kind of see the long list on the screen there of each, on paper, competitors now buddy in trying to get through compliance. And that makes a lot of sense. You know, if we're able to pool resources in a way that's mutually beneficial to everybody, now we can start to play around with some things and start to develop something like this. I mean, maybe Gary, do you want to explain this one a little bit more?
This is basically just a mock-up of what could be a new standard. So right now, the insulation standards listed in the building code, they stop at 706. So we're imagining 707, 26, so developed in 2026. And go ahead, Sam. And, you know, 708 would be a bat or blanket insulation. This one is interesting because there's already some development that could be leapfrogged on with Nature Fibers getting in Quebec getting CCMC evaluation for their bat product. So there's presumably some testing protocols and format already created that could be used to help develop the industry. And we're saying, you know, brought to you by this the Agricultural Biomass Manufacturers Association. Sam and I are still, you know, we're workshopping that.
We'll take audience feedback.
Yeah, definitely. Any suggestions are welcome. I think Sam had one that said A, B, C, D, which is really good too. Next slide. Yeah, so this is one that is likely it is being developed right now. I don't think it's going to have that number or the name. I don't know what the name will be, but it's being led in part by the Canadian Wood Council, and they're also open to other plant species. So not just limited to wood fiber. And there's still time remaining to get on to the ship and comment on how that standard develops, because often standards can be developed either intentionally or unintentionally to exclude certain products, materials, formats, and it's really good to have a say in the matter to make sure that there's no unnecessary exclusions happening. And ideally, we take all those standards and we put them into the building code right at the front there. They get added after the standards that are already in there. I think that's you, Sam.
Sorry, you kind of froze up there for a second. But yeah, now we need to make one, which fortunately we wouldn't be the first ones to do that. So there is an existing protocol. The biggest thing is essentially just figuring out what accredited laboratory testing do you need to do to determine that this material meets the functional statements of the building code. And does it protect occupants? Does it have a flame spread rating less than 500, meaning it's not going to literally explode if it's in a commercial building? And if you've taken time to read through some of these existing standards, you can see that it's not like you're reinventing the wheel with science. You know, if you go through the cellulose insulation standard, there's a test where they literally put a cigarette in a box of cellulose insulation, because I'm imagining someone up in the attic who decides to light up, and then they have burned down a few houses because of that. And so it's pretty reasonable things. It's not like, from how I've interpreted it, you're jumping through a bunch of different hoops. It's just going through, figuring out what are the reasonable applications of this product. How do we make sure it's going to perform moderately well? And then we get to spend a little bit of money, get an independent board together to review it, and hopefully it can be published and available to anyone to test to. It wouldn't be, you know, the company that supports its development has exclusive rights to be then, you know, developing this material. It would be anyone who wants to find their own way to make chopped straw insulation would be able to certify their plant to this standard. And kind of the last thing that we were thinking about with code compliance in general, in a Canadian context, would be looking at something like you have already with like ICF, foundations. It wasn't really something people really knew about like 20, 30 years ago. Now it's in the building code. Now it's a new, readily accepted form of construction that just over time gets included prescriptively in Part 9, or even with the International Code having a whole chapter dedicated to, or a whole appendix dedicated to prescriptive requirements of how to build a straw bale home. There's limitations. You can't go build a 6-story tall straw bale building without an engineer. But if you want to build a single story that meets certain requirements, you don't necessarily have to do all the fun stuff that Garrett and I have been talking about.
And I'll just jump in there, Sam. I think including some sort of natural fiber insulation construction method in the code can go a really long way in normalizing and proliferating that with builders that might not otherwise be aware of or comfortable with this type of construction, just like ICF has become more comfortable with many different builders. And it can kind of come from the top where regulation puts it there. And when people read the building code, they learn about how to build that way.
Mm-hmm. And for product manufacturers like Garrett, myself, likely even New Frameworks, it's when you develop what you want to be getting out into the market, come up with a testing protocol to make sure you're doing it the right way. It's pretty reasonable to have that be more standard based, have it more certification based. This is a product line or a manufacturing plant that third parties come in, make sure we're doing it correctly. With people out working in the field doing hands-on like straw bale construction, you could imagine that's like would never happen. So you would need to have something like an appendix in the code to really make it that form of building practice accessible to a wide range of projects. So it's something that wouldn't necessarily be needed for product manufacturers, but I think, and I'm sure there's folks in the room who know much more about this than me, because a lot of effort has already been put into it to incorporate some prescriptive requirements in an appendix so that you're able to just prove to the local inspector I'm doing it the right way, and off you go. You get to go build some stuff. But
So that's the. Go ahead, Sam.
I was just going to say that may not have been pretty as Jacob's presentation, but hopefully we got a few people thinking about regulation in Canada in particular, but even beyond, how I think we can make natural building materials very mainstream without a ton of effort. I think it's really close. It's just figuring out exactly what we want to be building, how we're going to build it, and then getting the rubber stamp on it being okay. Is we're not having to go lobby a bunch of people, to tell them that straw doesn't burn down. We don't need to change the building code to take out, fire protection requirements in residential. Like, you can just have straw be put out in the open and people can look at it with a pretty critical eye, and it's going to perform well. So that's why I'm very excited to see more efforts, more formal efforts being put together. And I would readily contribute to any group that would want to take this one step further and really formalize it. But
yeah, absolutely. And thank you very much.